So this is a spacecraft, not like legally or anything. It's not going to space, but functionally, this is all the core electronics you'd find in a real satellite. Flight computer, radios, power system, all wired together on a bench. I'm basically trying to build and operate it like it's real, just without the rocket. That's a little out of my budget. So what the is a flat sat? A flat sat is what you get when you take a spacecraft and you don't bother putting it on a spacecraft. Instead of packing everything into a nice compact structure, you lay out all the electronics flat on a table or rack, whatever, on a bench, and wire it up so you can actually poke and prod everything. Real missions use these to test software, debug hardware, and figure out what's broken before launch. Or, more importantly, after launch, when something breaks anyway. Because once your satellite's in orbit, you can't just open it up and poke around with oscilloscope probes. So this is where all the mistakes happen safely, and without having to make insurance claims. At the center of all this is the flight computer. It talks to everything else in the system. The main network here is a CAN bus, or controller area network. I think that's what it stands for. Basically, it's a really robust way for multiple devices to communicate on the same set of wires without stepping on each other. Then there are a few other interfaces like I2C and USB for simpler or lower speed connections. I'm using those here because I'm using a Raspberry Pi and it has those built in already. But on a real thing, you probably use CAN bus. In this case, even the CAN controller is actually connected over I2C, which is a little cursed, but it works. There's also a hardware watchdog, so that if the flight computer locks up, it gets automatically reset. Compared to a real spacecraft, though, this is simplified. No backup flight computer, no thermal control, no actuators like reaction wheels or thrusters or deployable things or anything like that. And almost everything is single string, so there's no redundancy, which is fine for a prototype, and absolutely not how you would ever want to fly. To actually operate something like this, you need more than just the hardware. You need some kind of mission control, right? This is OpenC3. It's the mission control software. It handles sending commands, receiving telemetry, logging data, and basically acting as the interface between you and the spacecraft. So instead of dealing with raw packets and binary data, you get something a little more usable. From here, you can send commands to the system, monitor telemetry in real time, and keep track of what everything's doing. So voltages, temperatures, system status, all of that shows up here. And this loop, send command, get data back, figure out what happened. That's basically how every spacecraft is operated. And here is the flat sat as it currently stands, minus electrical power system, which will be the next and probably the last major component. Anyway, I'll give you the quick rundown here. Bottom of this stack is Raspberry Pi 3B. Very old. Bought that for a security system thing like 7 years ago. Never used it. Finally found a good use. Below or above that is the sensor board that has the accelerometers and gyroscopes. So it's kind of like my IMU, inertial measurement unit. For some reason, it has this massive LED grid, which I had to physically disable by desoldering a resistor. It's really freaking obnoxious. These LEDs are as bright as the sun. So I don't know why they put that on a sensor board, but whatever. The sensors themselves work. And then above that, the little narrow board is the CAN bus controller. And above that is GNSS, which basically is GPS, but it talks to GPS satellites, Galileo satellites, and the Russian system, whatever the name is, I forget. It's got its own little antenna there. Over here is a hardware watchdog for the flight computer. See that green LED flashing once per second? That's actually being driven by the flight software on the Raspberry Pi. It's getting a heartbeat pulse from one of the GPIO pins on the Raspberry Pi. This is just an Arduino Uno. And if it stops seeing those rising edge pulses for more than 10 seconds, it will forcibly reboot the flight computer because, rebooting a computer in space is kind of hard. And then I got this massively overpowered Wi-Fi adapter to represent my high bandwidth communications link, which on a real spacecraft would be something like, I don't know, Globalstar or something. You'd probably talk to a big satellite in geostationary orbit that would give you much higher bandwidth than a typical RF connection. I had originally intended for this thing to become a high altitude balloon project, but I didn't want to spend all the money on this stuff and then just lose it in the ocean, which is probably what would happen. Over here, this is I'll call it the ADCS, or Attitude Determination Control System, even though the attitude is actually determined by the sensor board thing. This kind of represents a lot of actuators. The green LEDs here represent torque rods, which on a real spacecraft would be big electromagnets that produce a magnetic field that act against the magnetic field of the Earth, producing a torque on the spacecraft. The red LED represents a thruster. It could be like a Hall effect thruster or something like that. And then this whole thing works off of a Raspberry Pi Pico, and that talks to the main flight computer over CAN bus. And in the future, I'll have other things talking on that same CAN bus. This other Pi Pico is going to be the controller for the electrical power system once I get all the parts for that. And then I have this Amazon special cheap Baofeng dual band radio. I'm a ham radio operator, so I can use this. But I have two of these. I got a 2-pack on Amazon for like $30. So I have another one over here for connecting to my laptop. And my laptop has the OpenC3 and stuff on it. So far that seems to be working. I still need to add a bunch of stuff to flight software, but I have both comms links working. Typically on a spacecraft, you have the low bandwidth comms link, which kind of sucks, but you can use it more frequently. High bandwidth comms is more expensive and you can't use it as frequently, even though you have higher bandwidth. So you have both. You can send commands and telemetry with both of them. And then finally, I have the Raspberry Pi camera, because again, I bought this for a security system, never used it. Spacecraft, I don't know. I like engineering cameras on spacecraft because they help you diagnose problems, and not enough spacecraft have them. That's my excuse. So yeah, I have one. And focus. So yeah, there it is. It's all sitting on a silicone mat, soon to be permanently mounted in a small rack.
3, 2, 1, 0. Ignition.
Later, in the void. Later, in the void.
Is this an old message?
Later, in the void.